Powerful stuff. Do we have a, can I borrow the clicker? Thanks, yeah, grand. Okay. Thank you very much. Well, thank you very much indeed, Niels, for the invitation here and for the opportunity to talk to you all on the topic of achieving net zero by decarbonizing fossil fuels. And I was thinking, as I was listening to your opening about the history of this meeting, it is one of the reasons that we've made not as much progress as we'd hoped over the past 20 years in CCS, that it's been framed consistently as an environmental technology. But you could argue that CCS is an essential technology to protect the value of fossil fuel assets in a decarbonizing world. So it's a technology that an industry needs, rather than necessarily a technology that you see as a bolt-on environmental fix. And perhaps if we thought about CCS in that way from the outset, we might have made more progress. And so that's going to be the kind of topic I will be alluding to in my talk when I've finished initially talking about some of the key findings from the 1.5 degrees report. I was asked to start off. I was one of the coordinating lead authors of this report, which gave, I apologize on behalf of the report, some rather mixed messages about CCS. I think it did make so I will start with some uncontentious findings of the report, which I think are very helpful to this meeting. We're about 15 to 20 years away from 1.5 degrees at the current rate of warming, so we're now at 1 degree, warming at 0.2 degrees per decade. It's not difficult to work out the maths that we'll get to 1.5 degrees around 2040. That means we've got 30 to 40 years to reduce the rate of warming to zero if we're going to limit warming to 1.5 degrees. That's not a scenario or a model result, it's just geometry. That's what you need to do, how fast you need to bend the curve. And because carbon dioxide accumulates in the climate system, because we have this finite carbon budget, that means we have 30 to 40 years to reduce the rate of CO2 emission, net CO2 emission into the atmosphere to zero, if we start now. It's also important, this is a sort of, these are obvious points, I'm just really telling you, to remind you when you're discussing this, when you get out of this room, easy points to use to communicate. Every year's delay in reducing emissions means we have 2 years less to get emissions to zero, to achieve the 1.5 degree goal. That I find quite a useful image to give to people because it's the area under the curve that matters, the total amount of CO2 we dump in the atmosphere. The longer you put off starting reductions, the less time you have to reduce emissions, and you lose 2 years for every year's delay. And right now, emissions globally continue to rise. They haven't even started to fall. So why did I frame this in the way of decarbonizing fossil fuels? And so the first question to address is, do we actually need to decarbonize fossil fuels? And this is the area where I feel there were mixed messages coming out of the 1.5 degrees report. As Niels mentioned, there were 4 highlighted scenarios in that report, imaginatively named P1 to P4, which were scenarios which achieved the goal of limiting warming to 1.5 degrees. And in 3 of these, there was a very large role of both CCS and bioenergy with CCS, initially in decarbonization of the energy sector and subsequently in providing negative emissions to remove CO2 from the atmosphere. But the one that environmentalists and much of the press decided to focus on, so that yellow bands there in these diagrams show the CO2 removal by bioenergy with CCS. But let me point out in that P4 scenario that Niels mentioned, this black line is the net CO2 emissions into the atmosphere. Notice it leaves the gray, which is total CO2 production, very quickly. So there's a lot of CCS going on there, and then this is the big wedge of bioenergy with CCS. But everybody focused on that P1 scenario, which was deliberately constructed to show that it was possible to meet the goals of the Paris Climate Agreement without either BECCS or CCS. So the authors of that scenario, this is not the IPCC, the authors of the paper, were deliberately set out to address the question of whether it was possible to meet the Paris goals without CCS. And the question to ask ourselves is, does the existence of that scenario mean we can achieve the goals of the Paris Agreement without CCS or industrial carbon dioxide removal? This is the scenario I'm talking about, Grubler et al. In Nature Energy, published last year. Important to stress, this was not an IPCC scenario. The job of the IPCC is to assess the literature. This scenario existed, so the IPCC talked about it. It was published in a peer-reviewed paper. The IPCCs cannot ignore any paper that's published in the peer-reviewed literature. But it's important to understand this scenario was explicitly designed excluding CCS and CDR. It didn't ask the question of whether it made sense to exclude CCS or CDR. It asked the question of what would happen if you did. And one thing which came out very clearly from this is across all of the scenarios, we see a hard upper limit in how fast we can reduce carbon dioxide emissions. All the scenarios agree that we cannot reduce carbon dioxide emissions, whatever spectrum of technologies we adopt, we can't reduce emissions faster than 2 billion tons of CO2 per year. It's a rate of reduction in rate of emissions, that's why it's per year. And that's a really important number because that means we are now emitting at 40 billion tons of CO2 per year, slightly more. Even if we start emission reductions now, it'll take us 20 years to get emissions to zero. They will inevitably fall, the rate of reduction will fall as you're approaching zero, so we are committed at that rate of reduction to 1.5 degrees, even if we start reductions immediately. So, if we delay and adopt something like the P4 scenario, we're still limited to 2 billion tons of carbon dioxide per year. That's the limit to how fast we can get down emissions. And this, I should stress, is in these integrated assessment models. We've never done this, so we don't actually know whether we can even get to those rates of reduction. And what that means is if we are to limit warming to 1.5 degrees, every ton of CO2 that is dumped in the atmosphere before we start reducing at these kinds of rates is a ton that will have to be scrubbed back out of the atmosphere later on in the century. So this is the reality we're in. We're not reducing at that rate. Even if we do reduce at that rate, we will only just make the 1.5 degree goal. Therefore, we are committing ourselves to future carbon dioxide removal, which means geological disposal, to which the obvious path is through CCS. So I would put it to you, because I'm sure many of you go out of this room and then are dealing with environmentalists who are telling you, the IPCC said we can do this without CCS. Well, we can only do without CCS and industrial scale carbon dioxide removal if, in the P1 scenario, we reduce global per capita final energy demand by 30% between 2020 and 2030. You have to go into the small print to discover that's what happens in that scenario. But that's what goes on in this amazing decade between 2020 and 2030 in that scenario. And then to the environmentalists who are telling you this scenario means we can manage to meet the Paris goals without CCS and CDR, ask them, are we reducing energy demand, final energy demand? No, we don't even plan to reduce final energy demand globally. So we need CCS, CDR. It's that simple. And I'm sure it's very obvious to everybody in this room, but I'm pointing this out to you because the scenario was in there, in the IPCC report, and it is frequently waved around, certainly to me, as evidence that we can actually do this without CCS. We can't. To simplify the whole thing right down, so we're not relying on these scenarios, this is the situation we're in. This is a slightly unfamiliar way of presenting the climate challenge, but basically we have to get from A, where we are now, we are warming. This is not, normally people show you something plotted against time, but here instead I'm plotting the rate of warming, currently about 0.2 degrees per decade, against the warming, something physicists like to do. Okay? And it's if we want to limit warming to 1.5 degrees, we have to get the warming rate to 0 by the time global temperatures reach 1.5 degrees. That's just a geometric result. It's not a scenario, it's just what we have to do. That's what stopping the warming at 1.5 degrees means. Because the rate of warming is proportional to the rate of putting CO2 into the atmosphere, the annual rate of emissions of CO2, we also know that we have to reduce CO2 emissions, net CO2 emissions to 0 by the time global temperatures reach 1.5 degrees, if that is the agreed climate goal. Equally, we could say, in a very idealized world, suppose we just have a flat rate of CO2 emissions in business as usual. Suppose we manage through efficiency to maintain constant production of CO2, then getting net CO2 emissions to 0 means raising the fraction of carbon that we sequester as a fraction of the carbon burned to 100% by the time global temperatures reach 1.5 degrees. And suddenly we have a climate policy that's guaranteed to work. In that if you followed this trajectory, managed to raise the fraction of carbon you burn that you sequester, following that path such that it reaches 100% at the time global temperatures reach 1.5 degrees, then you would reach net 0 at the time temperatures reach 1.5 degrees, and you would meet your climate goals. It's a very simple policy. And we can now relate this policy to what happens in some sort of, as it were, real mitigation scenarios. So here's a whole bundle of these familiar mitigation scenarios from the IPCC, and these are the cost-effective well below 2 degree scenarios from the IPCC Fifth Assessment Report. They've been colored in by the cost of meeting climate goals, the cost of climate mitigation in these scenarios. And red is expensive, green is less expensive. Notice they all, these are well below 2 degrees, so these are not all 1.5 degree scenarios. Some of them are close to 1.5 degrees. They all go negative in the second half of this century because they all involve getting net emissions to 0 to stop the warming. Here's another way of plotting them. That different axis, the fraction of carbon that's burned that is sequestered. Okay, so it's exactly the same information plotted in a different way from the same scenarios, and you can see they all follow that pathway up to reach 100% at the time that global net emissions reach 0, because net 0 CO2 emissions means 100% carbon capture, net 100% carbon capture. That's what decarbonized fossil fuels means. One thing to notice here is that the bright red, the dark red scenarios, which correspond to annual costs of mitigation larger than the size of the world economy in 2010. Yeah, you should raise your eyebrows, okay? These are the scenarios where we are spending more on climate policy towards the end of the century than the size of the world economy in the 2010s. These are the really expensive, hard-to-believe scenarios. Okay? Notice which ones they are. They're the ones where we delay deployment of CCS. And this, for me, is the most worrying aspect of climate policy at the moment. Many people I talk to, including proponents of CCS, tell me it'll be okay when we get a proper carbon price, or when the ETS starts working, when the emission trading system starts working properly, it'll be okay. This is waiting for the carbon price or ETS to incentivize CCS. We've been waiting a long time here, and I don't want to spoil the outcome, but you all know what happens in this play. So let me just say, this is a way of avoiding that wait, okay? The blue scenario is that very simple picture where we have a quadratic increase in the sequestered fraction with warming. So we just say we want to get to, and this is a 2 degree quadratic increase, but you could adopt a 1.5 degree one, it would look much the same. So we say we want to get to 100%, so we follow this path of increasing the fraction of carbon that's burned, that is sequestered, and that keeps us on the safe side of this plume, away from those dark, angry red lines which correspond to very expensive mitigation later on this century. So here's a scenario for progressive CCS deployment. We are now at that purple dot in the corner. We're basically globally sequestering nothing, and we know we need to be sequestering everything by the time global temperatures reach our target well below 2 degrees. So we need to get to 1% by 2020, 2025, early 2020s. 15% or so by 2030 would keep us on this path. And we know that we need to get to 100% by the time temperatures reach 2 degrees or well below 2 degrees or whatever the final agreed temperature goal is. But we don't actually, I've dashed the line at the end there because we don't know exactly how long that will take. But if we get onto that path, the early stages of that path is the same regardless of the final destination. We got this close to making this happen in the UK in 2015. There was an amendment proposed to the UK Energy Bill to require importers and extractors of fossil fuels to contribute to the cost of carbon dioxide disposal. It was lobbied out. I don't know why, but although it was supported by all three major parties, somehow some lobby groups managed to get it killed. It is detailed how it would have worked, and I very much recommend this report from Ron Oxborough, who outlines this policy mechanism whereby you introduce an obligation on fossil fuel importers and extractors to sequester an increasing fraction of the carbon dioxide contained associated with the products they sell in order to ensure that we reach 100% sequestration by the time we reach our temperature goals. So how would this work? In particular in the Norwegian context, and now this is work I've been doing recently with Eli Mitchell-Larsen, who's going to wave at the moment, because if you want to follow up on this talk, I'm really sorry. I'm going to have to go at lunchtime today, but Eli is around for the whole meeting, so if you want to follow up on this, he's the person to talk to. How could we use this concept to introduce the notion of progressively decarbonizing fossil fuels, or green oil and gas, if you like? So here's two global temperature pathways. One, the light gray one, the thin lines, corresponding to the rest of the world not really doing anything, so temperatures just carry on at their current trajectory. Another, the optimistic one, where everybody joins in and temperatures are stabilized at 1.5 degrees. What that means is, as the fraction of carbon that we need to sequester following that quadratic path rises predictably over the next couple of decades to reach 100% at the time global temperatures reach 1.5 degrees. Notice that initially it doesn't make any difference which path you're on. Okay, whether the rest of the, doesn't make any difference what the rest of the world does. Norway or Equinor could get on this path tomorrow. It doesn't need to be conditional on what anybody else does. And what does that mean? For Equinor, I'm getting sort of personal here, but I hope that's okay. For Equinor to get on this path, it means that you need to increase the fraction of carbon you sequester as a fraction of total carbon that's extracted, so accounting for both Scope 1, Scope 2, and Scope 3 emissions, over time to match this path such that that fraction reaches 100% by the time global temperatures reach 1.5 degrees. Costs will, of course, rise. Initially, costs are quite low, so we've started off at the costs of Sleipner, disposal at Sleipner, and increasing to something like a free air capture cost when you get to the 100% capture at the end. But crucially, because you're only disposing of a small fraction of the carbon you dig up, the actual implied cost per ton of CO2 embedded in fossil carbon sold is much lower. That takes until the 2030s to actually reach levels of $50 per ton of CO2. These are the remarkable economics of mandatory sequestration. If we impose CCS as a mandate on the fossil fuel industry, that you sequester a steadily rising fraction of the carbon you dig up, then we reach equivalent carbon prices around $10 a ton in the early 2030s. That is far lower than the kind of carbon prices in conventional mitigation scenarios that are required to get us on a trajectory to 1.5 degrees. Notice the light blue, these are carbon prices. Notice that log scale, carbon prices going up to thousands of dollars per ton of CO2. Those correspond to those extraordinary, very expensive mitigation scenarios that I pointed out at the beginning of the talk. This is what you would need to do this. Norway has relatively few point sources of CO2. So in order to get on this path, you'd run out of CO2 very quickly. I'd say that's a good job. That's a good problem to have, but it does mean that the new proposals for importing CO2 to Norway and overcoming those problems with the London Protocol are absolutely essential to making this work. But just to wrap up, let me give you some simple facts to remember in an uncertain world. If we want to reach 1.5 degrees, we need to increase the fraction of carbon that's permanently sequestered, okay, by, on average, 20% per tenth of a degree of warming from now on. That's not a scenario, that's a fact. It's independent of any model, because that's just geometrically what you need to get to 100% in time. If we follow that quadratic pathway, that means we need to get to 16% sequestration by 2030, which is an extraordinary challenge, but if it were imposed on the industry consistently, that would imply a cost to the consumer that's lower than the current price of the European ETS. Why aren't we doing climate policy this way? So here's a question for you. How can oil and gas producing countries and companies best help deliver the goals of the Paris Climate Agreement? And the answer is not just by reducing their in-house Scope 1, Scope 2 emissions. People like to talk about this. It's what people feel that the countries own. But really, the main challenge for oil and gas producers is to decarbonize their products. And that means genuine, permanent geological offsets, not just accounting tricks like avoided deforestation. A progressive, verifiable, and trusted sequestration program would protect, crucially, the value of fossil fuel assets, and is therefore ultimately in the interests of the fossil fuel industry itself. And on that thought, I hope I've left a little bit of time for questions.
Thank you very much, Myles. That was a lot of food for thought. We don't really have time for questions, but I can allow one anyway. Is there a question?
Somebody from Equinor must be here.
Well, I don't have a question, but I have more a comment on the way you are showing this, you know, how these are new thinkings in my view, and I haven't seen that in the CCS kind of environment before, you know, so that's very useful, and a very clear message that we need to speed up on this technology as well. So.
Well, one thing, I mean, we are starting to see thinking on this in the policy regime. In the UK, there's a lot of interest in CCS certificate schemes to incentivize, because I think people recognize that CCS cannot rely on government subsidy forever. We need a long-term business model, and the only way of really getting that long-term business model in place that people have thought of is to tie CCS to the continued exploitation of fossil fuels. Mm.
Well, I agree, yeah, great. As a small token of appreciation, there is a gift there as well. Thank you very much, Myles. That's excellent.
Thank you.